Hey guys, welcome back to Computational Biology with Python. In this lecture, we're going to be going over how to convert files and some other things with multiple sequence alignment files. We'll start with converting and we'll see what we get through. Depends how many typos I have, right? So let's go ahead and jump on in. Alright, so start out from bio import align IO if you're just starting up with me again. How about we capitalize bio like it should be? There we go. All right, now let's do count equals align IO dot convert. We're going to convert our PF 05371 seed .sth. And we're going to do stock home, and we're going to convert it to a file called PF 05371 seed .aln, or an alignment file, which is a cluster file. And we have to tell it that it's a cluster file. Oh, I love when it works the first time. So you should see we have this alignment file, and you can see it's formatted differently here. Unfortunately, let's see, I don't think, yeah. So it puts the first however many characters here, and then the next on the next line. This isn't the greatest length for an example, but you can see an alignment. You can see where there is indels, right? Insertions, deletions. So here, either these are insertions or these are deletions, etc. Okay, so that's how we convert to a cluster W file. We can also print converted %i, so the number of alignments, and then count. So we converted one alignment. So I guess if we had a loop, we could convert more alignments. Okay, so let's look at alignment equals align.io.read. Hold on a second. So you can also do it this way. Let's see. Oh, that's why I skipped some stuff. We can do this as well. So alignments equals align io.parse PF 05371 c.sth. This is a Stockholm file, and then we can say count equals align io dot write alignments PF 05371 seed .aln, and then cluster, run that, and then we could do print converted I alignments. Don't put that comma there. Count. So there's more than one way to skin a cat. That's what I'm getting at with this. Okay, so I'm not gonna. Here's actually I have another example too, but you don't need. It's just the same thing, but just there's a lot of things in coding, especially in bioinformatics, that like there's no wrong way to do it as long as your end product is what you're looking for. I mean, there's some snobby people that'll be like, oh, this is hacked code, like hacked together. But if it works, it works. That's all I gotta say. So whatever method you choose. We could also make a Philip format. So we can convert to that. So PF05371 C.STH stack home, and then we'll call this one PF05371 seed.phy, and we'll call this is a Philip file that we're making. And then, so now over here we have this Philip file for the same thing. So there's multiple ways you can really save anything. Let's see. So as you can see, these are broken into like these 10 character chunks, and it's not super so the sequence so the problem is that the sequence identifiers are truncated as well, so it takes everything in there. Oops, don't save that. Close without saving. Okay. Even the sequence identifiers are truncated at 10 chunks. So it's just part of this Philip file format, I guess is the best word. So we can do something similar. I'm just going to copy this and paste it right here. And I'm going to change it to Philip's relaxed. So if we run this, and now we open this Philip one, you can see it puts in the entire sample name. So different options depending on what you your preference. Let's see. We can also manipulate the identifiers or the names of the files. So if we do alignment equals align io.read, and we read in PF05371 C.STH, and we tell it it's a stack home. And then we can do name mapping equals, and we do 2 curly brackets. And then we say for I record in enumerate alignment name mapping I equals record ID equals seek, and then the I. So what we're doing here is we're going to number our sequences, and then I. So if you run this, because I have a space there. Okay. Record ID equals. Oh, I'm missing. There we go. How about that? Okay, so now if we print name mapping, you can see that we've numbered, all right, 0 is the first element, 1 is the second element, Python numbering, and we've numbered all these elements. So we can also do then align io.write alignment pf 05371 c.phy, and we do phylip. And so let's look at this file now. So now you see that we've added what sequence number before the file. So we have sequence 0, 1, 2, 3, 4, 5, and 6 before the file by this chunk of code right here. So that might, if you have like a whole bunch, especially if you get to the point where you're like, okay, I want to extract one of these sequences, and you're working with like 100 sequences, it's nice to have a number so you can know what line number to take out, right? So that makes it a little more convenient. Okay, what are we at? 10 minutes, okay. Do we want to... Alright, let's do some slicing alignments. So, what's our alignment? What do we have here? That's not what we need. Okay, so let's do alignment equals align io dot read. Let's read in our Stockholm file. Okay, so print number of rows, and then as an integer, right? So %i, and then length of alignment, alignment. What? Oh, it's supposed to be, wait. And like that. There we go. Number of rows, 7. Okay. So now for record in alignment, print a string and record.seek record ID. Oh, what did I do? Minus s percent. Oh, how about we put these in the right order? Okay. So now, let's do something like this. Print. So this has been saved this as like a list. So now if we do print alignment 3 through 7, you can see that we have 3, 4, or no, this would be, yeah, 3 through the end, 3, 4, 5, 6, and it's not inclusive of 7 because we start with counting 0, right? Okay, so that's 3 through 7. You can do that for any number. So this is where I said like the line numbers is nice, right? Because if you wanted to know what number co-protein. And as you can see too, something we've done different I forgot to mention on this bit of code is depending on how you print these, or print these in this regard right here, you can have the name of the sample at the end or the name of the sample at the beginning, etc. So you can kind of move those around. So we have them at the end this time. Before, I think at the top they were up at the beginning. Okay. Let's do this. Print alignment 2, 6. So hold on a second. Let me make sure I'm in the right spot here. Okay, so what this does is, this is the column in the row, right? So you're picking from here. Okay, so what this is saying is pick out the second row. Remember, we count 0, 1, 2, this row, this alignment, and then pick the 6 characters, 0, 1, 2, 3, 4, 5, 6. So that gives us our T there. Another way to do it would be to do this. Print alignment 2, seek 6 should give us the same thing. Yep, T, perfect. You can also pull out a single column, so we can do print alignment. So if you were interested in, all the snips at one position, you could do something like this, and you can see that it just prints TTT dash 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 T. TTT dash 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 T. So you can see all the different snips at those positions. You can also select a range. So say we want to print alignment 3 through 6, and so we just picked the rows 3 through numbers, alignments 3 through 6, so 0, 1, 2, 3. So wait, 0, 1, 2, 3, and then we picked the first 6 letters, right? So that would be 1, 2, 3, 4, 5, 6. So that's how you get that. So whenever you leave the first index, so print alignment as the colon, that means take all the rows, right? So this is saying take all the alignments and then pick everything through 6. So that's the first 6 characters of all the, or first 6 amino acids through all the alignments. So let's do print alignment everything, and then 6 through 9. So this is a good way. So say you want to remove a section of the alignment, right? So in this case, we're like, okay, I'm gonna get rid of everything that has a gap here. So these 3 characters, TSQ, TSY, TNY, TNY, and then the dashes. So you can just pull out those 3 letters for later removal. Let's do what if we wanted to get everything after the 9th column? We could do something like this. So you can have it afterwards, right? So we've been doing it before. We said, okay, everything before 6, everything before 6, etc. Well, you can also do it after, right? So print the alignment, everything after the 9th column. There we go. So everything after the 9th letter. You can also remove blocks of columns. So edited equals alignment, and we'll say everything before 6, and alignment is everything after 9. So now if we print edited, we should have a sequence you can see. So let's see, 0, 1, 2, 3, 4, 5, 6. So it dismisses the 6th one. Oh, wait, why is it 43 columns? Four, 6. Oh, sorry. This is all the columns and just the first 6 letters. Why is... Okay, I figured out what I was doing wrong. I was comparing to the wrong thing. So let's compare up here. So this is everything. AEPNAAT. So we've done AEPNAAT. And then we have gotten rid of NYAT, or NYA, the next NYA, and we spliced in this EAMDS. So that's how you splice. So it was confusing because I thought this was the full sequence when I was looking at it. I was like, why is this not right? Okay, let's do... we removed a block of columns, and then let's do one last thing. We can do edit, sort, and then, oh, sorry. We did, okay, we have edited, so that's our one with our splice there. We can do edited, sort, and then we can print edited. And so what this does is it sorts so it sorts based on the name of the by ID, which would be was it this, was ID the second one? Say, oh, right here, this one. Yeah, ID, so it's the last, so it sorted by the numbers, right? So 30, and it, no, it didn't, it sorted by this. So it's not super intuitive for this because the numbers are in there, right? But so BPI 22 numbers come first, then BPIF, then BPIK, then BPM, then BPZ. So it's descending alphabetically that way. So might make more sense if you had like species names or something like that. Excuse me. But you can do it. I just want to show you can do it. So we're gonna stop because I think we're just about at our time limit here. So thank you for watching. I hope you learned a little bit of something. We will, I promise, get into actually creating alignments ourselves, but right now we're just kind of playing with alignment files, which are important. They're important for evolutionary biology, for identifying causal SNPs. So if you identify a point mutation in a BRCA gene or something like that, this is where that comes from. So thanks again for watching. Please hit like, please hit subscribe. It really helps me out, and I will catch you in the next video. And again, back to hitting the wrong one. Bye.